Let's talk about the fundamental theorem of calculus, part 1. So this is the part of the fundamental theorem that says what you see at the top of the page here. If you have a function that's continuous on a closed interval, and you make this new other function out of its integral, so g of x would be the integral from a to x of f of t dt. So this weird kind of integral function is continuous and differentiable on your interval. And the part that we use the most is that the derivative of this function would be this integrand function with an x in it that you use to start the whole thing. Okay, so above the line here on my page, I have two straightforward applications of this theorem. So first we have g of x is the integral from 0 to x of e to the t dt, and we're asked to find g prime of x. All right, so this theorem says it's going to be the integrand that's in this integral right here, but with an x as the variable. So instead of e to the t, I'll write e to the x, and I'm done. Same thing with this second one. It doesn't really matter that the definite integral starts at 5 and this one started at 0. It really doesn't matter what that number a is right there. It's all about the rate of change of this function. So again, we're going to take this integrand formula and just put an x in as its variable. So here my derivative is the square root of x squared plus 1. Okay, so these are two straightforward uses of the theorem. And what I have below the line here are some less conventional uses of the theorem. All right, so let's start with this first one here. So we're still being given an integral function and asked for its derivative. But what makes this one really different from the two before it is the x cubed right here. So because we have an x cubed in the spot where the theorem covers just an x, we want to see this as composition. So the outer function of my composition here is the integral function. And then the inner function is this here. And I'm going to do the chain rule for its derivative. So the outer function's derivative would be sine of x, but I'm going to have the x cubed plug in it for my f prime of g. So that's sine of x cubed. And then I'll multiply times the derivative of the x cubed to get 3x squared. So this is f prime of g times g prime. All right, let's try another one. Again, here we have an integral function and we're asked for its derivative. But this has the same problem as the other one and another issue here. So the fundamental theorem only applies to integral functions where the input x is the upper bound of the integral here. So what we need to do is see this that way. So it's a problem that the x is at the bottom bound instead of the top, and we also have the square root of x instead of a regular x. So the first thing I'll do is switch the bounds. We know that if you switch the bounds of a definite integral, it's at the expense of a minus sign. So now I have a minus sign out front. Everything else will stay the same. That minus sign is going to carry down into my derivative. And then again, I'll do this derivative as a chain rule. So the integral function, 1 to x, is my outer function, f. And then my inner function would be this root x right here. So I want to do f prime of g times g prime, much like we did up here. So f prime would be the derivative of the integral function. So that's ln of x. But it's f prime of g, so I'm going to have a root x plugged in. And then times g prime will be times the derivative of that root x, which is 1/2 x to the negative 1/2. All right. My last example kind of has every possible issue. So we don't have just an x as the upper bound. We have a formula of x, and we have x's in both bounds of integration here. So we can't differentiate rather. So d dx means differentiate this whole thing. So it's still the same problem assignment, just written differently. But we can't do that until we split these up into two separate issues. So I'm going to pick a number. Any number will do. Usually 0 is my default to split this integral in two. So I'm going to have d dx, that means derivative of the integral from 2x to 0 of this function plus the integral 0 to x squared of this function. And we know from properties of definite integrals that this plus this is still the original function. And again, there's nothing really special about the 0 that I chose. Any number in this spot will do as long as it's the same number here and here. Okay, so I have one more step before I can do the chain rule derivatives, and that's going to be just to do the switcheroo on these bounds to get the 2x to be the upper bound, much like we did over here. So I'll have negative integral 0 to 2x, and everything else will stay the same. Now I can do separate derivatives on this integral and this integral function. So this first one, the minus sign carries down immediately. And then again, I have a composition here, so I'll use the chain rule, f prime of g times g prime. The outer function is the integral function, so its derivative is tangent of x. So my f prime of g is tangent of 2x times the derivative of 2x, which is 2. And then very similarly for this second one, the derivative of the integral function would be tangent of x, so I have tangent of x squared times the derivative of the x squared, which is 2x.